GameSci.com. GameSci.com.
Yo, what's up, people? Let's talk about Python variables. According to dictionary.com, a variable is likely to change or vary, subject to variation, or changeable. My definition is I've always thought of a variable as a location in computer memory where I can store something, a cubbyhole, a little spot where I can store a value for later use. X position equals 4. We're going to assign the value 4 to the variable x position, and you could see that a 4, or the binary value that represents 4, gets stored into computer memory. Y position equals 5. Let's store a 5 in the variable y position. Again, it's a small piece of computer memory where I can store values for later use. I'm storing the value 5 for later use. Money equals 20.0. 20.0. That's a little bit different. We're storing a number with a decimal point this time. You notice I made the memory a little bit larger because it needs more memory to store a number with decimal points. Let's store a float value, a number with a decimal point, in computer memory. All I'm doing on all of these examples is storing values in RAM memory for later use, because that's what a variable does. It reserves a spot in RAM memory for storing your value. Name equals double quote Zork, end of double quote. Whenever you put something in quotes, it's a string value, and Python will allocate memory to hold a string of characters. Now, see that red box? This is the memory that's been allocated to store my character Zork. This is a different type than an int or a float. It stores letters, not numbers. Paid user equals true. This is a Boolean data type. Python has a data type where you can store just true or just false in it. I decided to assign true, so a value representing true is stored in RAM memory for later use. Now go back to the original definition, likely to change or vary. Let's change one of our variables and see what happens. What you'll notice is assignments in Python are what we call destructive. I said x position equals 6, and it stored a 6 in that piece of RAM memory that used to hold 4, and the 6 overwrote the 4. Assignments in Python are destructive. When you assign a new value to a variable, it replaces what was previously stored in the variable. The 4 is gone and the 6 replaces it. So that wraps it up for our intro to variables. We'll learn much more in the next slide. The thing I want you to understand is variables are just a spot in computer memory where I can store values. Name, type, and value. Variables have a name. Descriptive names are good. Short abbreviated names are bad. Give your variables a name that describes what you're storing in the variable. Variables have a type. What are you storing? A whole number? A number with a decimal point? Letters? True, false? What are you storing? That is the type of your variable. Variables have a value. What is the current contents of the space allocated? Variables have name, type, and value attributes associated with them. Score equals 0. Store the value 0 in the variable score. In this case, the variable name is score. The value is 0. Python decides based on the context the type of the variable. This happens to be an int variable or integer. It's a number with no decimal point. That is an integer. What you assign to the variable determines the type. Python is what we call a loosely typed language, and whatever you assign it, the variable takes that type. Health equals 100, and you could see that 100 gets stored into the health variable. In this case, the variable's name is health. The value, the current value, is 100. Python decides based on the context the type of the variable. In this case, we're talking about an int or integer value. It's a number with no decimal point. What you assign to the variable determines its type. Score and health are integers because we assign them integer values, numbers without decimal points. Strength equals 0.47, and a 0.47 gets stored into RAM memory. The variable in this case is strength. Its value is 0.47. This is a float. A float is a number with a decimal point. It's also known as a floating point value or a double in some other computer languages. Python has many different data types for its variables. Integer and float are just two of the types Python supports. Type equals double quote ogre, end of double quote. This time we're storing letters into RAM memory. OGRE is a string of letters that we are storing in the type variable. The name of the variable is type. The value is ogre. Python decides based on context the type. There's nothing more important than these quotes. Anything in quotes Python treats as a string. Officially, the data type is str, but everybody calls it a string. Anything in quotes is a string. Even if you put the number 1, 2, 3 in single quotes, it is a string. It is not a number. Anything in double quotes or single quotes, Python treats as a string of characters. Now, variables have a type, what you're storing, a whole number, a decimal number, letters, true or false. Now, notice I called this variable type. And I wanted to bring it back to video games, because in video games you battle various types of enemies. You'll battle ogres, or dwarfs, or trolls. They're different types of enemies, and we've come to understand that. What I'm trying to get you to understand is variables in Python have types too. Instead of ogres, trolls, and dwarfs, like we battle in a video game, Python has variables like ints, floats, strings, and booleans. The most common data types in Python are the int or integer data type, a number with no decimal point, float or floating point, that's a number with a decimal point, an str, which is the official name, and string is what everybody calls it. Anything in quotes, double quotes or single quotes, is a string value no matter what. And finally, the bool, B-O-O-L, or Boolean data type. The only thing you can assign to this type of variable is the value true or the value false. The three most important things to remember about variables is they have a name, sometimes called the identifier, a type, and a value. Always be aware of all three things when dealing with variables in Python. Changing variables. Let's see how we can change variables, because part of the definition of a variable is it's something that can change, it can vary. It's where it gets its name from. So let's see how we can change variables. We'll start out with an x position equal to 1 and store a 1 in RAM memory in our x position variable. Now I drew a little character down here at sort of x coordinate 1. Just to show you the value in the x position determines where the character is going to be shown on the screen. Now I'm going to say x position equals x position plus 2. First, I extract the value 1 from the x position variable. After I extract the 1, I add a 2 to it. I come up with 3, and I store the result 3 back into the x position variable. So this becomes 1 plus 2 equals 3, and a 3 shows back up in RAM. Now, since the character reflects the value of the variable, I just move the character to position 3 on the x-axis. The x-axis is fairly big chunks here. That'd be x0, x1, x2, and x3. That's the position that the character is drawn at, x position 3. Once again, I'll say x position equals x position plus something. Again, I have to extract the value stored in the variable. Variables are a two-way street. You put stuff in them, you pull stuff out. In order to evaluate this expression, I pull the value 3 out of the x position variable first. After I pull the 3 out, I add a 1 to the 3, come up with a 4, and store the result back into x position. And my character moved to a new position, x position 4 on the x-axis. Another way to adjust the variable is to use variables to change the value. So I'm going to set up a speed variable equal to 3 and store 3 in RAM memory, and that will determine how fast my character moves. Because in the next equation, I'll do x position plus speed. I'll grab the 4 out of x position, the 3 out of speed, add them together, come up with a 7, and do what with the 7? Assign it to the x position variable. So after I'm done extracting the two values, I'll add them together, come up with a new value for x position, and store it back into the x position variable. And you can see my character jumped all the way to x position 7 on the screen. Now the reason I'm going to use a variable for the speed and adjust it by the speed, that means I can have a character that moves slower or faster. I can also move it a different direction. I'm going to set speed equal to -2 and store -2 here in the speed variable. And this time, when I say x position plus speed, I'm adding -2 to it. So I'm doing 7 plus -2, and guess what's going to happen? I'm going to move my character the opposite direction. When I do x position plus speed, 7 plus -2 comes out to 5, and I move left on the x-axis. Store a 5 in the x position variable, and you can see my character jump backwards or towards the left. By using a speed variable rather than hard-coded values, I can move the character in both directions without changing the code or the equation. Now you'll notice that this variable is a little bit different. Start x equals 2. Python has a convention. The convention in Python is if you give a variable name in all uppercase letters, it becomes what's called a constant or a final variable. The signal on that is we should not change the value of start x. Now there's no enforcement mechanism in it, but if you give your variable an uppercase name, it says I want to store 2 in this variable, and I always want to store a 2. I never want to store anything else but 2 in this variable. And that's so we can have a constant place where we start our character. If we want our character to start at position 2 at the beginning of the level, we set it equal to start x, and it'll start at position 2. All right, so that was a little example of what variables do best. They change, they vary. A good variable is supposed to change values, especially variables that control the positions of characters on your video game. They're supposed to change values, and what I did there is run through a lot of equations that alter the x position and move the character about the screen. Global versus local. Variables come in two categories, a global and a local. Global var equals 66. You can see we're storing the value 66 into our variable, into our RAM memory. Now this is declared outside the function. It makes it a global variable. Print outside the function global variable contains. The function main is skipped and will not execute until it's called. Indentation is important. All this code that is indented will be skipped. Code outside functions execute first as soon as the program runs. This is outside the function, it executes. Then we find the next line of code that's outside a function and it executes. And the code outside the function will execute before the code inside of a function does. And all we're doing here is we're printing or outputting the value of global variable. And you can see at the very beginning we have a 66 stored in our variable. This is a call to the function main. This will make the code inside main run. You'll see the arrow I put here. When you call the function main, it will jump up here and execute the code in main. Inside main, I'm going to say local var equals 99. And then 99 gets stored in the variable local var. This is a variable created inside a function. Variables created inside of a function are local. Variables created outside of functions are global. Local var was created inside of mains. It does not exist until main executes. It is local. Notice how this didn't even pop up until we ran main. It can only be used inside the function that is created. So this variable is only good inside of main. We're still inside the function main. Notice the indented code. Indented code is very important. Everything that is indented after the definition of main is part of main. These blank lines don't matter. What really matters is the indentation. This line is indented, it's part of main. This line is indented, it's part of main. So let's print this line. Print inside the function. output the local variable and the global variable. And you can see here on the output inside the function, the local variable is set to 99 and the global variable is 66. It retrieved the values from these variables in RAM memory and output them to the screen. Code inside the function can access both the local and the global variables. The last line of code of the function main will return to the point after main was called. Watch the local var over here. Watch what happens when we return. So why is this the last line of the function main? Because it's the last indented line underneath the definition of main. Main will contain all the indented lines, and when you're done with indented lines, main is done. And that's why this arrow is saying is once you're done with this line, jump back to whoever called main. It'll jump back to after the call to main here. Notice first that local var was deallocated. We had a variable called local var, and it went poof, it disappeared. When a function returns, its local variables go away. Global variables stick around. They'll exist as long as the program is running. But local variables, like this guy right here, get created when main runs and they disappear when main finishes. When I'm coming back here, after the function runs, I'm printing after the function the global var contains 66. And that's the only thing I can print. I cannot print local var because local var does not exist outside of main. You'll recall I left some blank lines up here. I left a blank line here and I left a blank line here. I'm going to add more code to this to more explain how locals and globals work. I'm going to run it again, but this time I'm going to add a new line of code. I'm going to say global var equals 77, and I'm going to put a local or global with a question mark here because I'm not quite sure. This is a warning. Watch carefully how the variables work in this case, because something strange is going to happen here. This is one of the things Python does a little bit weird that we have to know about it. Let's start with global var equals 66, and you can see that I have a 66 in my global var. I'll print outside the function and global var 66 will show up. I'll call main and run main just like we did before. But now watch carefully what happens. I say local var equals 99, and just like last time, local var is created inside of main. It does not exist until main executes. That's why it's called a local variable. It can only be used inside the function that gets created. Local var is clearly a local variable. But watch what happens next. I say global var equals 77. What? This turns out that this is a new local variable. Just because it's called the same name as this one up here doesn't mean it's the same variable. So when I say global var equals 77, it basically does the same thing it did on the line before, and it says, well, I'll create a brand new local variable. No matter what its name is, it's going to create a local variable, and it's going to store the 77 in the local variable, not in the global variable. Even though it has the same name as the global variable, Python still makes a local variable. That's why I've been warning you on this slide. You have to be very careful on understanding what's global and what's local. Even though I named it the same thing, it is not the same variable. This is a local variable. And you'll see when I print them out, inside the function, the local var has the 99. Global var has a 77. Now, where did that 77 come from? It's important to understand it came from this second copy of global var, and it took the 77 and output it to the screen. Since a local was created with the same name, the print will use the local version that contains 77 of the variable. This is a warning. You have to be very careful how you use global variables because you might end up using a local instead. After the functions, you'll see that the local var was deallocated just like before. And then this new copy of global var, the one that contained a 77, that got deallocated too. When a function returns, its local variables go away. So this is why you have to be careful. The global still exists. The original global variable up here with 66 still exists. And the 66 that was in it got printed out down here. But you've got to be careful on what is a global variable and what is a local variable. Be careful, the global still exists, maybe with a different value than you expected. Don't worry, there's a fix for this, and the fix is coming right now. There is a special global keyword that makes sure we do not create a new local variable. In this case, by putting global var here, we're saying I explicitly want to use this variable right here. I do not want to create a new local, so use the global version of it. This keyword makes sure that we do not create a new local variable. In this case, the 66 is in the true global variable, is going to be replaced with a 77. It is a good idea to use the global keyword every time you want to access a global variable. If you create global variables at the top, make sure you use this global line in every function that's going to use that global variable. Use this line every time you want to access a global variable. Now, required if you plan to change the global variable. Turns out you don't have to use this global line if all you're going to do is print or use the variable. This becomes critical when it comes time to changing the global variable. If you don't use this line, it will create a new version. Now, it's not required to use the global keyword to access a global, but even if you only plan to access it, go ahead and use that global line. If you are expecting to use a variable that was declared at the top inside of a function, go ahead and use that global keyword. Let's do some math on Python variables. One of the things we do most with numeric variables is change their values using mathematical equations or expressions. Let's set up a few variables here at the top. We'll set minutes equal to 0 and seconds equal to 0. Now what did I do here? Notice that semicolon. Python does not require using semicolons at the end of the line unless you want to put two equations on the same line. The reason I have to put a semicolon here is so I can do this. I was running out of room on this slide and I didn't want to use two lines of code. I don't like doing this. I don't like putting a semicolon and two separate lines of code on the same line, but it is possible. I'll set minutes equal to 0, seconds equal to 0, and you can see my variables contain zeros. Note the semicolon. You can place two lines of code on the same line if you separate them using a semicolon. Time equals 125. You can see that the 125 gets stored into computer memory. This is 125 total seconds. Inside a computer memory, the computer doesn't track hours, minutes, seconds. The computer tracks seconds. And what we're going to do here is use the seconds to calculate hours and minutes and seconds. Integer divisions. Minutes equals time divide 60. The two division symbols next to each other say I want to do integer arithmetic. What does that mean, integer arithmetic? Well, often when you divide two numbers, you get a fractional result. You get a number with a decimal point. However, sometimes you don't want that. You want the whole number. When 60 gets divided into 125, it goes into it twice. And what integer arithmetic says is I want the 2. And you could see that the 2 shows up. Does everyone see this on the equation? 60 divided by 125 gets divided into it twice. All I want is the 2. I do not want the decimal point after the division. And that's what the two divides next to each other does. Say, well, throw away the fraction. I just want to know how many times 60 divides into time. And the answer is 2, and 2 shows up in the variable. Well, how do I know the leftover seconds? We're going to use something called the remainder or the modulus operator. We're going to do time modulus 60. Now, what does the modulus operator do? It calculates the remainder after the division. So when 60 divides into 125, it divides in it twice. But we subtract out the 120, 2 times 60, and we have a remainder of 5 after the division. When you do integer arithmetic, there are technically two answers. There's how many times the numbers divide and what's left over after the division. Two divides next to each other says, give me the whole number, how many times do they divide? The modulus operator says, give me the remainder that's left over. Integer division gives us this answer, and the modulus gives us that answer. Turns out 125 seconds represents 2 minutes and 5 seconds. Pretty easy math, I think. Test equals 3, semicolon, test plus equals 4. Now I'm trying to jam a lot of commands in here. That's why I'm using the semicolon. I don't really want you to use the semicolon, but you can use it when you want to put multiple lines of code on the same line. Test equals 3 will store a 3 into computer memory for me, and there's my 3. Then I'm going to do a new expression here, test plus equals 4. This is called a shorthand assignment operator. We want to do an operation on and store the result in the same variable. So what this is equivalent to is test equals test plus 4. Since we're often add a value to the current variable and store the result back in, this is just a shorter way to type in this expression right there. So what you should read this as is test equals test plus 4, and 3 plus 4 comes out to be a 7. Test 2 equals 6. Simple assignment of the value 6 to the variable test 2. Then I'll do another shorthand assignment operator. Test 2 multiply equals 3. A shorthand assignment operator basically does a 6 times 3 and stores the 18 back into test 2. This expression right here in the red box is the exact same thing as if I'd written test 2 equals test 2 times 3. Another example, test equals test divided by 2. This is our normal division operator. It could also be written as test divide equals 2. And I put a note here, type change. It's a warning. Be careful. A single divide slash returns a float. 7 divided by 2 is 3.5. A variable has just changed type from int to float. The variable test before this line of code executed contained a 7. If you look at the line above here, test contained a 7. But 7 divided by 2 has a fractional result. It's 3.5. What happened here, you got to be very careful about doing this, is my variable just changed from type int to type float. When you do division, the results, normal division, the result is always a floating point number. That's why we have two different division symbols. With 2 slashes, you're doing integer division and your result would be an integer. With a single slash, you're doing normal floating point division and your result is going to be a floating point value. Test equals round of test. Now we want to change it back to an integer. We decided we made a mistake by turning it into a float. So what we're going to do is we're going to round the result and round it back to a number. Now 3.5 turns out rounds to the value 4. Variable test now contains an integer again. The one thing you really have to be careful in Python is the type of the variable. If you accidentally change the type to something else, it could cause problems later in the program. So once you create something as an integer, you kind of want to keep it an integer. Test 2 equals 2 multiply multiply 4. Multiply is the exponent operator. This is 2 raised to the 4th power, which is 16. This is saying raise my value to a power. 2 to the 4th power is a 16, and a 16 shows up here in test 2. Now, I went through a lot of the different operators. Of course, Python supports the normal arithmetic operators of plus, minus, multiply, and divide. But they also have these special ones, the integer division operator, the modulus operator, and now the exponent operator. You can see we can do lots of different mathematical equations on Python number variables, but I warned you about the type. Remember that? You better be using numeric types when you use any of these arithmetic operators. If somehow you accidentally changed a variable to a string from an integer and then did arithmetic on it, Python program would blow up and terminate. So you have to be aware of the type before you use these arithmetic operators. Python operators work on numbers. They don't work on strings. String objects. Strings are objects in Python. To be honest with you, all variables are objects in Python, but we won't get into that till a later time. Python variables are what we call references. Name is a reference variable, which means they point to or refer to objects. When you assign a value to a variable, it technically goes in the object the variable points to. What do I mean by that? Let's take a look. Name equals Mario, and Mario gets stored into a string object. And then name references that string object. Name is pointing to or referring to that variable. This is how Python really stores values in variables. It creates an object of that type, an int object, a float object, a string object in this type, stores the data in the object, and then the variable just points to or refers to that object. Now I'm going to say name equals name plus brothers. I'm going to add the word brothers to the current name, which is Mario, and Mario Brothers gets stored into the object. And what you'll notice here is for strings, Python does support the plus operator. This becomes what we call string concatenation. I want to add a string on the end of the current string. So currently name contains Mario Brothers. I want to concatenate or append a 2 to that. When the plus is between two strings, Python will append the strings and make a larger string. So all that happened is the Mario Brothers got a 2 appended to the end of it. That's what the plus operator does when it's a string. This is why you have to worry about the type of the variable. The plus operator will work with strings. Length equals len of name. Len is a built-in Java function that will tell you the length of something. The length of Mario Brothers 2 is 14. There are 14 characters in this string if you count them. 1, 2, 3, dot, dot. This is the 14th character in the string. Length, or len, will return the size of the string, and a 14 gets assigned to the variable length. Here's what really makes a string an object. I'm going to say name equals name dot upper. I want to convert name to uppercase characters. What's going on here? This dot operator says go to my object reference name, go inside of it, and run a method called upper, which will convert it to uppercase. It took Mario Brothers and set it to all uppercase letters and stored the result back into the name variable. This is what we call a method, and the dot operator says go run this method, convert it to uppercase, store the result back into the name variable, and you could see all uppercase letters are now stored into our variable. Here's another method. I'm going to go to the name variable and I'm going to find the string bro inside that object. So it goes inside here and it looks for bro and it finds it right there. There's a bro in the name variable. And where did it find it at? It found it at character number 5. Now why is this character 5? Because character strings start with 0. The M is at character 0, the A is at character 1, the R is at character 2, and it turns out the B in bro is at character 5 of the string. Well, that 5 gets returned and assigned to the variable offset, and you can see a 5 shows up in the variable offset. It's a little tricky. You got to remember that strings start at character 0, not character 1. My bool equals name dot starts with of M. What you're going to do is go to the name variable. The dot says go inside this object, run the starts with method, and look to see if it starts with an M. And sure enough, this string starts with the letter M. So the starts with method will return a true. My bool contains the value of true. If the string started with something other than M, this would return a false. Name equals name dot replace 2, 3. I want to replace the character 2 with the character 3. And there you go. A 2 got replaced with a 3. All of these things, upper, find, starts with, and replace, these are what's called methods. When you have an object, you can run its methods to do things on that object. And we did several things like converting uppercase and replacing characters and finding characters. Turns out in Python, all strings are objects. It turns out all variables are objects, to be honest with you. But strings are the most obvious example that we want to get into now. As we move farther along, we'll explain how Python variables work and more details on how Python objects work. One more slide to wrap this up. Syntax, runtime, and logic errors. Errors. They are going to happen. The ability to find and fix them is the key to being a good programmer. No one types in perfect code. The three types of errors we'll look at here, from easiest to find and fix to the hardest, are syntax errors, runtime errors, and logic errors. Let's take a quick look. The program to the left here has problems. It intentionally has problems. Let's see how we can fix them. Start with the easy one, syntax errors. They're the easiest to find and fix. If you are using a decent IDE text editor, it will light up with a red squiggly line, then hover over the line and will usually provide a decent error message. Clearly what we're missing here is an open parentheses. Syntax errors must be fixed before the program will run. If you try to run the program without fixing it, an immediate error message appears. What we're missing here is a parentheses right there. That is called a syntax error. We basically typed in the code wrong. When you type in miscellaneous characters or wrong characters, it's a syntax error. The program won't run. You have to fix it before you can go on. Notice I fixed the syntax error. I have to do this or the code will not run until I do. Again, a decent IDE text editor will light up with a red squiggly line, then hover over that line and it will usually provide you with a decent error message. It'll say, hey, you're missing a parentheses. Next up is the second syntax error. The second syntax error is down here. Clearly, we have the very common bad indentation problem. Remember, it is extremely picky about the indentation. You have to have perfect indentation inside of a function. You have to have good indentation outside the function. Because these lines, this one, and this one, are not indented the same, Python is pointing to the line that is not indented properly and saying you have an error. This is a syntax error. It has to be fixed. It's pretty clear, especially when it comes to indent. If you type in the indent wrong, it's going to stop and say you have to fix it before we go on. Notice how I fixed the indent problem with main. I scooted it over a little bit, and now it lines up perfectly with the other ones. That syntax error is done. You cannot run the first line of code until all the syntax errors are fixed, and there's nothing wrong with this first line of code. So once I've fixed my two syntax errors, that one and that one, now it will actually try to run the program. And just to be nice to you, we did a fine thing with the first line. Age equals 19 is nothing wrong with that, so we'll assign a 19 to it. We've got no errors. Let's go on. Technically, there's nothing wrong with this line of code. But good variable names often provide important clues. X position, Y position are usually coordinates and numbers. I'm a little leery of these double quotes right here. X position to me should be a number. X coordinate 0, X coordinate 10, X coordinate 20. It should be a number. Those double quotes are worrying me a little bit. So even though this line of code works properly, you got to be careful here. These are the letters 47, not the number 47. So although this line executes, I'm suspicious that it's a string data type. Incorrect types are a common Python runtime error. You got to be very careful of the types when it comes to Python. Crash! Runtime error. Program will terminate. What happened here? Runtime errors occur during program execution and stop the program in the middle of the run. The error in this case was a type mismatch. X position is a string. We tried to add an int to it, and that is an illegal operation. This is why it's so important to pay attention to the types of variables. I was worrying about this line and worrying about this line, and I was wondering if that should be a string or an int. I left it a string, but obviously down here we thought it was an int. String plus int is a runtime error. It's a type mismatch. This is why it's so important to understand what the type of each variable is. This is a good call to the main function. I fixed the indent, the previous syntax error, so this is good. But let's go back and look at the previous bug where I put double quotes around this one to get this line of code to work and not crash. It now works, but maybe I fixed the wrong thing. Maybe the real fix was up here. Maybe this should be an int. I should lose the quotes here, make this an int, and then add a plain old integer 1 down here. Sometimes the error occurs on a previous line, but is not revealed till later. This is a domino effect. I made a mistake up here that is affecting code down here. When that happens, you got to look at both places. Now I chose to fix it here, and we'll stick with it, and we'll go on, but we'll see how that might affect the code later on. We made the jump to main and we're executing the code in main. This line is fine. Once again, there was a previous syntax error on this line, but it's fixed now. So it executes and outputs the words hello world. Crash, another bug, a runtime error. The program will terminate. This is the classic divide by zero runtime error. You cannot divide by zero. This is an undefined number, and Python and just about every programming language will crash when this occurs. Runtime errors occur during program execution and stop the program in the middle of the run. There is no saving this line of code. We're going to have to delete it. The harder problem is when you do a divide by a variable and that variable sometimes contains a zero. I made it very obvious here by hard coding the zero. But if we had a variable here on this side of the divide, and sometimes it contains zero, then sometimes it would crash. But if most of the time it didn't contain a zero, most of the time it wouldn't crash. So you got to be very careful when you're doing division that you don't divide by zero. We finish main, we return to the main program, and we print age and X position. With logic errors, the program runs, unlike with syntax errors. Logic errors don't crash the program, unlike runtime errors. Logic errors means the code produced the wrong result, usually by executing the wrong code. Recall my bad fix of putting double quotes around this one. If X position should have been changed to an int, it would now be 48 and not 471. What if the map only had a width of 100? Then obviously a width of 471 would be bad. Again, I talked about this several times. Maybe this should be an int, and then this should be an int. This is a logic error. I was expecting a 48 in this variable, and I got a 471. When you look at the printout, age and X position, I got age is 19 and X position is 471. Maybe X position should have been 48. This is what a logic error is. Your program runs, it doesn't crash, but it produces incorrect results. This would be especially true if my map was smaller. Let's say I had a map on X from 0 to 100. Obviously, an X position of 471 would be taking my character way off the edge of the map. So you have to be careful. Logic errors are tricky. Getting good at fixing errors should be your highest priority. No one types in perfect code. For syntax errors, make sure you use a good IDE editor with color highlighting and clear error messages. Runtime errors, look closely at the line where it crashes, but sometimes it is a previous line. And finally, with logic errors, know your domain. Learn how to spot results that are out of line. You must know what your variables should contain so you can spot problems when they contain illegal values. That's it for this lesson. Have a good day. We'll see you on the next one.